Hey everyone, so it is 4.2 now, adding, subtracting, and multiplying polynomials. Now the rules for adding and subtracting and multiplying polynomials follows what we've done before, and it's pretty much combined like terms. Now there's two ways you can do this. You can do it the horizontal way, which is just having them all in one line, or you can line them up vertically. So I'm going to leave that one right there, and then the second option is 3x cubed plus 2x squared minus x minus 7, and then I'm going to line them up. So that's x cubed with x cubed minus 10x squared, and then it's going to be nothing here, so I'm just going to put in a 0 as a placeholder, and then plus 8. Now when I combine them, what's going to happen, I'm going to do negative 7 plus 8, which gives me a plus 1. There's nothing happening with that x, so it stays as a negative x. And then I have negative 10x squared plus 2x squared, so that's the same thing as saying 10 minus 2, which gives me 8x squared, and then 3x cubed plus of x cubed. Remember that there is always a 1 there, so you end up with 4x cubed. And I should have changed colors, but I wasn't paying attention. So that is the vertical format. The horizontal, like I said, is just combining your like terms. And that's all you have to do. Now, when it comes to subtraction, it is the same idea. However, the order does matter. Remember that whenever you add or multiply, order does not matter, but division and subtraction is very important. So in this problem, I am subtracting 3z squared plus z minus 4 from 2z squared plus 3z. So again, I can either have it as 2z squared plus 3z minus 3z squared plus z minus 4, and then I would go ahead and distribute that negative to get 2z squared plus 3z minus 3z squared minus z plus 4. And then it's combining like terms, but if I wanted to set it up in the vertical, I would have 2z squared plus 3z minus, and again line them up, 3z squared. So the reason I don't really like the vertical for the subtraction is because you have to remember that your signs are going to be changing. So you want to have that negative on the outside, just so that way when you do the subtraction, it's really 2z squared minus 3z squared, which, as we can see here, we have a 2z squared and a negative 3z squared, which leaves me with negative z squared. Then I have a plus 3z minus z, so again, this is 3z minus positive z squared, and that positive and a negative is always a negative. So 3 minus 1 is going to be a plus 2z. And that negative 4, there's nothing to combine with it, so negative negative gives me a plus 4, right? So as you can see, same steps that we have done, there's nothing out of the ordinary for this. Now, when it comes to multiplying, same idea. Now, what you can do here for the multiplication is you have two options. Personally, I distribute one term at a time and then combine the like terms. However, you can actually do 3y squared times that y plus 5. It's the same idea, right? So I would do 3y cubed, because I'm multiplying y and 3y squared, and then y and negative 2y is going to give me negative 2y squared. and then plus a 2y. Then it's going to be a plus 15y squared minus 10y plus 10. I ran out of space there, but you get the idea. So there's no other 3y cubed, so I'm going to keep it exactly where it is. So 3y cubed. Then I have a negative 2y squared and a plus 15, so 15 minus 2 is 13y squared. And then I have 2y minus 10y, which we kind of already did a problem like that earlier. That gives me that negative 8y. And then there are no other constants, so that plus 10 stays on the end. Again, same thing that we've been doing. There's nothing different about what we are doing. Now, when it comes to multiplying three binomials, the best way to go about this is to do FOIL for two of the binomials. Now, it does not matter which two you pick. You can pick the first two, you can pick the last two, you can pick the ones on the outside. I don't really care. The point is that you're multiplying, so again, order does not matter. But I'm going to stick to doing the first two, so I'm going to go ahead and FOIL that. Gives me x squared plus 4x minus x minus 4. And I keep that in parentheses. I'm going to have that plus 5 there at the end. And that's going to give me x squared plus 3x minus 4 times x plus 5. So now I'm going to distribute, just like I did in the example above, all my x's, so x cubed plus 3x squared minus 4x, and that's going to be a plus 5x squared plus 15x minus 20. Now I combine my terms. There's no other x cubed, so it stays. Then I have 3x squared and a 5x squared. Both of them are positive, so plus 8x squared. Then I have negative 4x plus 15, so 15 minus 4 is going to give me a plus 11x. And again, there's nothing with that constant, so the negative 20 stays there. And that's all you have to do to multiply three binomials. Now, there are some special product patterns. As you can see, you have a sum and difference, square of a binomial, and the cube of a binomial. Now, these are all very helpful to know, but basically just as a shortcut. You can easily figure out this information without remembering the exact pattern. It's just to save you time. So if you do memorize them, saves you time. If not, you can still just FOIL and you will get the same result. Now, proving a polynomial identity. I'm sure some of you all thought you were out of doing proofs because we are out of geometry, but this is a very simple one, and all I'm going to do is that multiplying by three binomials to prove to you guys that a plus b cubed is going to equal a cubed plus 3a squared b plus 3ab squared plus b cubed. Now, all of those letters sound very, very strange. I will tell you that we are going to cover something in this section that will make more sense of what's happening with all those ABs going on. So I wouldn't worry too much about it because we will go over that. So I have just gone ahead and FOILed my first two terms. Oops. Now I'm going to FOIL with the third one, or distribute the third one. So a cubed plus 2a squared b plus ab squared. Then I'm going to have a squared b plus 2ab squared. Oh, and I'm running out of room. Plus b cubed. We'll have to throw that one down there. Now I'm going to look for like terms. So a cubed stays by itself. Now I'm looking for an a squared plus, times b. There's another one. So that's going to give me a plus 3a squared b. Then I have 2ab squared plus an ab squared. That's going to give me another 3ab squared. And then once again, there's nothing with that constant. So b cubed stays at the end. So if you notice, that is exactly what we were told. So just by foiling the binomials, you can get the exact answer. Now, using the special product patterns, so this is where if you remember them, it's nice and easy because you don't have to waste your time foiling. So in this case, if I look over here, I'm looking at a sum and difference. So when I have a sum and difference, what's going to happen is I'm going to basically have a squared minus b squared, right? A squared minus b squared. But a is represented by this 4n and b is 5. So I would have 4n squared minus 5 squared. So 4n squared, when I do a 4n squared, what's happening is that I am actually distributing that exponent to both the 4 and the n. So I would end up with 16n squared minus 25. And that is all you have to do. If you want to do it the other way by foiling, you can. If you multiply that, you'd get 16n squared minus 20n plus 20n minus 25, and these middle terms are going to cancel out, leaving me with just that 16n squared minus 25. Okay? Now, the last thing to discuss in this chapter is called Pascal's triangle. It is a very special pattern that helps you expand binomials, right? Right now we're only looking at, something to the third power, but what happens if it is to the fifth power or the sixth power, right? You can't spend your whole time just foiling. So this is where Pascal's triangle comes into play. It is a very nifty little array of numbers such that the numbers in the nth row are the coefficients of the terms in the expansion of a plus b n for whole number values of n. Now, Pascal's triangle, it starts with a 1. That's what I have here at the top, 1, right? This is when I have my n, my a plus b to the 0 power, right? Anything to the 0 power is just 1. Now, when I have a plus b to the first power, right? Anything to the first power is just itself. So 1a, 1b. Okay? Now, I'm going to keep going. If I have a plus b squared, what's going to happen is I draw that 1 first. I'm always going to start with a 1, okay? Then, what I'm actually going to do is add those coefficients from before. So that's going to be 1 plus 1, which is 2. Actually, let me change that to 2. And this is going to be a squared. Okay, and then at that 2, we're going to have a and b. Okay, and I'll explain what's happening with those variables and why some of them have the degrees and some of them don't. But essentially, it is a pattern. You're starting at that term, so this is a squared binomial, so I start with the first term having an a squared, and that value decreases by 1 every time I move along the triangle, right? So let's say I had a plus b cubed, right? So once again, I start with the 1, combine 2 plus 1 is 3, again, 2 plus 1 is 3, and then again there's the 1 on the outside. So If I'm doing my variables, this is going to be a cubed, this is a squared, a to the 1, and then a 0. I don't have to write that a to the 0. Now my b's go in the opposite direction. So I'm going to start this last one with b cubed. Then I'm going to become b squared, followed by b, and then no other terms, right? And I keep going. So if I wanted to the 4th, I would have 1, and then I would combine. I have 1. 1 plus 3 is 4. And then I have 3 plus 3, which is 6. 3 plus 1, which is 4 again, and then 1 again. So this pattern continues, and we will be practicing Pascal's while we're doing this section. Now, as you can see, using Pascal's triangle, the first thing I want to do is create the triangle. Now, I'm not going to really do that because I just did it in the previous example, so that's where I'm going to look. And I'm looking at a third expansion, meaning that what I'm looking at is a cubed plus 3a squared b plus 3ab squared plus b cubed. Now, I personally prefer writing it in terms of a and b. When I see that, it is much simpler for me to look at. And I know that I'm going to be replacing every a with 3y and every b with 1. So I would have 3y cubed plus 3 times 3y squared times 1 plus 3 times 3y times 1 squared plus 1 cubed. So now is when I'm going to go ahead and simplify. So 3 squared is going to give me, 3 cubed is 3 times 3 is 9, times 3 again is 27y. Okay, now here in this second term, I have 3 times 3y squared. So this is going to really be 3 times 9y squared. And that's actually a y cubed there. So when I do that, 3 times 9 is once again 27y squared. And remember that 1 isn't changing anything. Now for this next term, I have 3 times 3, which is a 9y, and last plus 1. So that is how you use Pascal's triangle in order to expand binomials.